So let's go over quiz 3. And this is mostly about the same stuff that was on quiz 2, just with curvilinear coordinates. So in fact, maybe problem 1 was even kind of a head smacker if you didn't go back over quiz 2, because basically the same questions were just in for A, spherical polar coordinates, and for B, cylindrical coordinates. So the question is whether or not these vector fields are conservative, and what conservative means still is it has no curl. So we're asking whether or not the curl of G or the curl of F vanish everywhere, which is through Stokes' theorem equivalent to saying that contour integrals are completely independent of path and they only depend on the endpoints. So let's start with F, and all I have to do is figure out what coordinate system I'm in. And oops, there was this little typo that got corrected, but I didn't correct that here. So that is phi hat. Figure out what coordinate system we're in, and then write down the appropriate expression for the curl in that coordinate system. So F is in spherical polar coordinates, r, theta, phi. And in general, what we have is we have this overall scale factor. And then for curl, we have scale factors that show up. And again, this is one way of writing it, this determinant form. Scale factors show up with the unit vectors, and scale factors show up in the components themselves. And we'll just dot, dot, dot. So this is dq1, and then h1, q1, and then likewise all the way across there. Okay. So for spherical polar, we have a scale factor. R is already in units of length. For theta, we have r. R theta is a unit of length that's appropriate. And for the phi coordinate, we project down into the xy plane. So that's r sine theta. So overall, the product of those is r squared, r times r sine. And then pro tip, write the components first. So we have scale factor times the first component. That's minus r cosine theta. Scale factor times the second component. That's r times r, or r cubed. And then third component, we have r sine theta sine phi. So r sine theta sine phi, which is sine phi. And then d by dr, d by d theta, and d by d phi. And this is 1 times r hat, this is r times theta hat, and then this is r sine theta times phi hat. Okay, kind of grubby, but it turns out that a lot of these things don't depend on the other variables, so we have no d by d phi for 2 of them, which makes it not as bad as it might look. And then what you end up with overall is dot, dot, dot. So I think I was pretty forgiving about calculus mistakes, provided you actually wrote the correct form of the determinant in spherical polar coordinates. So you should get minus r sine phi r cotangent theta. And then I think this is probably not the most simplified way of writing it, but I think probably one that everybody should be able to factor into or out of on their own answers, and then 3r, that at least was nice. So this is definitely not equal to 0, and this is definitely a non-conservative function. So we are off the hook from having to find its potential function. Okay, same thing here, but now we have cylindrical coordinates. We have rho phi z, which actually is a little bit easier. And honestly, the trick that I kind of embedded in this is if you wrote down the Cartesian form of the curl, you didn't put in the scale factors, your punishment, as well as losing some points, was that this would actually look like it was a conservative function without those scale factors, and you would have had to find the, on your own merits of your own logic, you would have had to find the potential function. Does not have a potential function. Turns out not to be conservative as well because of scale factors. So again, we have product of all the scale factors. Scale factor for rho is 1. It's already got units of length. Likewise for z. So we really just end up with rho because rho d phi is an actual unit of length. Again, pro tip, write the components first. So no scale factor again for rho. So that is z over rho quantity squared cosine phi. We do have a scale factor for the second component, the phi component. So that's minus rho times z over rho squared sine phi. And then last component, no scale factor, is z over rho cosine phi. And again, d by d rho, d by d phi, d by dz, rho hat, no scale factor, r phi hat, sorry, rho phi hat, scale factor for only the thing in units of radians, and then k hat or z hat, whatever you feel like calling it. And then, again, not as bad as, actually this one's a little bit grubby because there is a 0 and r for all of them, but all the terms basically look alike. So it's all, basically you take many copies of the same derivative. And what you should get, if you did it right, is a non-conservative function that almost vanishes. So you should add 2 terms, one that was minus z over rho squared sine phi for the first term, and then minus 2 or plus 2 of the same thing. So close to vanishing, but not vanishing. And then likewise, we have the same thing cos, and then one of these was nice and vanished, but also non-conservative. So again, the mistake is if you didn't realize that this was in curvilinear coordinates and use the appropriate form of the curl, you wouldn't have put in these factors, and the function itself was designed to vanish in that case. And then you would have had to write down the gradient, which if you made that mistake, you probably also didn't write down the gradient in curvilinear coordinates and then integrate it, which actually wouldn't have been too bad. So that is question 1. Same thing, we just have curvilinear coordinates. Okay, question 2. Again, a lot like a question that we had on the last quiz, where there's a vector function. This time it's in spherical polar coordinates, and there's a surface, and you're asked to compute the flux. And always in your back pocket, you have, in this case, the divergence theorem. If we were asking about a curl through a surface, probably not a closed surface, we'd have Stokes' theorem at our disposal. But you do know this if you need it. I'm skeptical that I will need to use this because this function actually looks pretty grubby, and I don't think the divergence, especially because the divergence would need to be expressed in spherical polar coordinates, might help me. But before I make that choice, I'm going to write down what this surface that I'm integrating over is. So I have the surface x squared plus y squared plus z squared is r squared, which is the surface of a sphere of radius r. Okay, and what is the surface element of such a surface? So it's a little piece that looks like this, and it points in the r hat direction, right? No matter where I am on the surface, I'm going to point in the r hat direction. This, to me, is the key piece of reasoning in realizing that maybe I don't want to use the divergence theorem, because what this is saying essentially is that if d sigma is, whatever the size of that thing is, and it points in the r hat direction, I only pick off this piece. So I only pick off the r hat piece. I don't have to worry about the phi hat and the theta hat pieces. So 2/3 of my problem disappears. So I think that the divergence theorem is kind of a, red herring here. So what is this? Well, same logic. This would be the 2 scale factors times the pieces themselves. The surface itself, we don't change in R, but we do go all the way around the surface. So we go all the way around phi and theta. So in fact, what this turns out to be is r d theta, r sine theta d phi, just the usual scale factors, and the fact that the surface changes in theta and phi, but not r, but it does point in the r hat direction. Okay. So putting that all together, I have this, and I'm tempted, but ultimately choose not to use the divergence theorem. This is a tractable problem with the divergence theorem. It would have taken a bit longer, maybe more than a bit longer. Just writing down my surface integral off the bat, I go all the way around the sphere, so that's 0 to 2 pi in the phi coordinate and 0 to pi in the theta coordinate, and then alpha 2 cosine theta over r squared. That's the r hat piece, because all we dot out is the r hat piece, so we only care about that. And then our d sigma, our area piece, is r times sine theta, so r squared sine theta. And then d theta, d phi, making sure I've got these ordered properly. And a lot of really nice things happen. So again, you could do this with the divergence theorem, but in this case, you're rewarded for realizing this was easy, or rewarded for forgetting the divergence theorem. I don't know, however you want to think about it. Let's pull that alpha out, and then we get 0 to 2 pi, 0 to pi, 2 cosine theta sine theta, d theta, d phi. Okay, and this is just the derivative of sine squared. So we can antiderivative that and get sine squared. And then there are no phi pieces, so the integral over phi just gives us a 2 pi. So that's 2 pi alpha, and then sine squared theta evaluated at pi and 0, and sine squared evaluated at pi and 0 is both 0, so that's big fat 0. Okay, so this is actually a really complicated looking vector field, but it turns out that the flux through the surface is 0. If we were in an electromagnetics class, you would deduce that there was no net charge inside the surface if this was an electric field, A. But basically set up so that some magic cancellation happens. It's actually all these problems. And in this case, 0. Easier here if you use the divergence theorem, harder, but still possible. And then finally, 3. I'm going to do this one the hardest way possible. So the part B is really just picking off the fact that the scale factors are given to you. Part A, I totally would accept the logic that these are parabolas and these are ellipses. If you understood, identified which ones are the parabolas and ellipses, great. I'm going to do this the hard way. I want to know where the unit vectors u and v are. So the unit vectors u and v are the vectors that tell you in what direction does u increase and v increase. And honestly, I don't have to be too precise about this because, for instance, these curves don't look too exotic. So let me just pick some point in the first quadrant. So let me just pick a point like, they're about even. And I know if I want to get in the first quadrant, x and y need to be positive. And looking at these equations, I could do that by having u and v positive and by having u greater than v. So I'm just going to pick a point and then show how I would manually determine which way u and v are if I couldn't just look at those and say, aha, this is my parabola and this is my hyperbola, which to be honest isn't, or my ellipse, which to be honest isn't like 100% clear. Okay, so let me find a point somewhere snugly in the first quadrant, again, by choosing u and v positive and then u greater than v. So I don't trust myself to do math, so I have this written down. And I guess I picked u equals 4 and v equals 2, sure. Which corresponds, if you plug these in, just plugging them in, to the point x equals 6 and y equals 8. Okay, so that's like in the neighborhood of point P. And these things don't act in a complicated way around there, so I think we're good enough. So the question is, how would I, if I didn't know how to read the equations directly, how would I find u hat? Well, u hat is the direction where u is increasing. So let me just do the exact same thing and make u not equal to 4, but equal to 4.1 and keep v the same. So I'm going to give away a little bit of the answer here. Essentially what I'm doing is I'm staying along one of these lines of constant v, and I'm increasing, I'm going to the next line of constant u. Right. So I'm staying along the line of constant v and increasing u. Now that might not necessarily be exactly where we're at, but that's the idea. And those might not be u and v. We'll see in a second. Okay. So increase u, keep v constant, and then perform the same calculation, just dump them into our formulas. And what you get is, okay, not an elegant number, but it's good enough. So we get to the point 10.510 is x and y. And then let's say I want to go to v hat, or figure out which way a vector points if v increases. So let's keep u the same as our initial point, and then v is 2 plus 1. And then that's, call it 3.512. Okay, so we're somewhere around here, and then u hat points in such a direction as both x and y increase. So that's definitely this direction, x and y increase perpendicular to the line of constant u, going in the direction where u increases. So this is u hat, surprise, surprise. And then v hat points in the direction where y increases and x decreases. So that looks like it fits the bill. So if I wasn't 100% sure, these are points that just verify my intuition. Okay, and then the question is, okay, sketch and label the unit vectors. We did that. We did more work than we needed to be honest. And then which way does z point? Well, z points out of the board, so are we in a left or right-handed coordinate system? So u cross v points out of the board, z points out of the board. We are in a a right-handed coordinate system. So u cross v equals z hat, or k hat if you want to call it that. Okay. And then the last question is basically read off this. So you're given this thing, which means more than maybe you think it is. So we haven't talked about metric tensors yet, but we want to write an expression for the divergence of some function of vector function of f, u, v, and z. And the generic formula is for something in curvilinear coordinates, divergence of some vector function f is 1 over h1, h2, h3. So the product of the scale factors, and then this kind of cyclic permutation, v1, h2, h3. This is the easy one to write. Partial derivative with respect to the second coordinate, v2, h1, h3. And am I going to run out of room? Yes, I am. Partial derivative with respect to the third coordinate, v3, h1, h2. Okay. And then filling that in, what are the scale factors? Well, this is h1. This is h2. And this is h3, which is 1. Okay. And h1 and h2 are the same thing, so this actually turns out to be really pleasant. Just multiply that by itself. So it's 1 over u squared plus v squared. And then d by du, u component times scale factor 2 times scale factor 3, which is square root v1 plus v2 squared. We should probably use parentheses for these to be more clear. Plus d by dv, the v component of the vector function, times scale factor 1 times scale factor 3. Scale factor 1 is that. Scale factor 3 is 1. And then plus d by dz fz times scale factor 1, scale factor 2, which is u squared plus v squared. Okay. Looks a little bit messy, but honestly, all it was identifying the scale factors from the line element and then plugging them into the divergence formula. And kind of the intuition that you should be developing before we get into metric tensors is that if you tell me the formula for the curl, or you tell me the formula for the divergence, or you tell me the formula for the line element, I should be able to figure out, or the gradient for that matter, if you just give me one of those, I should be able to figure out the rest. So it's almost like there's this like kind of master information in these scale factors that tell you everything you need to know about the coordinate system. And it's true.